Section 8.7, velocity, acceleration, and the distance from a particle from a reference point. We'll call it the origin. We're headed to Granny's house. Got the greatest pecan pie in the world. So we head out on the interstate highway, but after a while we realized, oh, we forgot our son Johnny. So we had to go back and get Johnny, and then we started going again. So what we were doing was we were heading in a positive direction, but then we came back a negative direction in reference to our house, and then we finally went back to Granny's. When we got there, she was in bed with long ears and big teeth, and you know the story. Anyway, so then here's a graph. You want to make sense out of graphs in all of life. You look at the x and the y-axis. This is time in hours. This is distance traveled, S of t. So hey, we were traveling along maybe 85 miles an hour, realized we forgot Johnny, went back home and picked him up. Do you notice that this positive slope is not as steep as this negative slope? That implied, yeah, maybe we were traveling 85 miles an hour, but when we went back towards the house, we might have been going over 100 miles an hour, don't tell anybody, but we were going in a negative direction. So this was negative velocity, but it was faster than when we were going in the positive direction away from the house. Speed is the absolute value of velocity. So this speed was positive, going in a positive direction. This speed was bigger than this speed. I said that wrong. This is velocity. This velocity is positive. This velocity is negative. But this negative velocity, its absolute value, was bigger than the absolute value of the positive, so that its speed was faster. All right, let's look at and here we can think of a couple of things. The original function is the distance by the time we've traveled t hours. The first derivative is the velocity. Now it's velocity at t hours. So like right at this point in time, after 1 hour, 2 hours, we're still tooling along at 85 miles an hour on the highway. That didn't change. Oh, acceleration is the rate of change of the rate of change. We weren't changing our velocity. We weren't speeding up, and we weren't slowing down for this period of time. So we had zero acceleration. We weren't changing in either direction. So if you think about it, if you take a look at this green line, the original function, S of t, was linear. It was how many miles you travel. The first derivative of linear would be the speed at which we're traveling. Velocity is miles per hour, 85 miles per hour. If you take a derivative of 85 of any constant, you get zero. That meant that our acceleration was zero. And that would be our rate of change of the rate of change. And so acceleration is miles per hour, or miles per hour squared. If that makes sense, fine. If not, not a huge deal. You just want to make sure that you know the original function is distance away from whatever your reference point is. First derivative, velocity. Second derivative is acceleration. All right, let's look at a problem similar to the one we see in our homework in section 8.7. So this is the distance of a mosquito away from this lamppost. Clearly that's a lamppost, it's not a cigarette stuck in the ground. All right, now we see the y-intercept is negative 32. That means the bug is starting 32 feet to the left of the lamppost. And what it's going to do is it's going to fly on to the right of it, back to the left, back to the right again. So where that bug goes distance-wise in relation to that zero is shown here. And so what we can do, provided our calculator is nice to us, please, you gotta talk nice to the calculator, it's like a plant or something. We're going to look at this function and let's wrap our brains around what this function is telling us. When a function is positive, it's its y value. We know that this in the y direction is the distance in relation to that guy. So we started out at negative 32 feet. That meant 32 feet to the left of this. That's why the y-intercept for this cubic is at negative 32. Hey, when we get to zero, that means the mosquito made it to the lamppost. It kept going. So it has a positive distance in reference to what we call our origin. And then, so hopefully we can make sense of that. Now let's look at a couple other things. Do we agree that its velocity is speeding up? Velocity is positive when we're heading to the right. So our slopes of our tangent lines are positive in here, so it's heading to the right. Then it stops at a positive distance, so the mosquito stops up here somewhere and comes back to the left. Then it's negative velocity down in here, then positive velocity up there. So let's bring in the acceleration function. Let's add it to our graph in red, and let's see what that looks like. Sure enough, we need to reconcile the fact that this velocity function is above the x-axis, meaning the velocities are positive whenever the mosquito is moving to the right. And so the mosquito here is moving to the right. It started at negative 32 feet, it made up to 0 feet, and even went past the lamppost. That's why the velocity function has values above the x-axis up in here. If you want to make a first derivative chart, like we did before, which can help us make sense out of that, this value, where the velocity goes to 0, which happens to be when the mosquito turns around, is at 2.31 seconds. You can get that off your calculator. And then the velocity comes back to being positive again at 6.36 seconds. And so what we can say is, looking at this graph here, we can see that it's positive slopes, negative slopes, positive slopes. That means the mosquito is traveling to the right, then to the left, then back to the right. And we see we can reconcile that with the blue graph also. It's moving in a positive direction, then it stops. It moves in a negative direction, then it stops, and it goes in a positive direction. So we should be able to reconcile those. Now let's bring in the acceleration function, but let's anticipate a little bit. We see that this blue graph is concave down. That means in relation to moving right or left on here, it's actually slowing down. It was really going pretty fast right at the beginning. You see the velocity was really a strong positive velocity, but you can see the graph is curving downward. So the velocity is slowing down. That's why the red curve is getting lower and lower and lower. And it's going fast, but it's slowing down until the mosquito stops, and then it comes backwards. That's when the velocity is actually negative. It's coming in the backwards direction. So it's concave down until we get to a point of inflection in here, and then it's concave up. So it's actually going, the mosquito is going very fast, it slows down, it's coming back this way, and then it slows down, and then it's going to speed up again. So at a point of inflection here, it starts speeding up because it's coming back below 0, but it's slowing to a stop and then going back in the positive direction. So there's a lot to see from that, but let's see if we can then add the acceleration function and wrap our brains around what we're seeing there. So now we have the original 2 function, and there comes the acceleration function. That graph, the acceleration was below 0, it was negative when it was concave down, meaning that our velocity is either becoming a smaller positive or a bigger negative. So it's slowing down, then we're speeding, then our velocity is increasing in the positive direction. We've got to be very careful when we use the term speed and velocity. I should check myself that speed is the absolute value of the velocity, so you can be speeding up going in the negative direction. So when we're talking about acceleration being positive, that would imply that the acceleration is increasing in the positive direction. So after this is concave down, then it goes concave up. That means it's slowing down, coming this way in the negative direction, speeding up, going in the positive direction, so it's concave up. So if you look at the blue graph in terms of its concavity and the point of inflection where it turns and goes back up, we can see that the acceleration makes sense, concave down until right there, then concave up afterwards. The acceleration function is positive. If you can wrap your brains around that, then answering the questions you'll be asked of in the homework and just about movement by a particle in general becomes so much easier. Instead of memorizing, I think it's better to make sure that we really understand what's going on, and then we can just check our understanding as we go through. So let's see how that works. Some of the problems we're going to see, and we could write this down, this next derivative is obviously going to be 6t minus 26, so that is the acceleration function. You solve for 0, you get 4 1/3, so you can see that's where the inflection point is, where it goes concave down to concave up. So now let's look at some of the questions we might be asked. At what time or times will the particle be left of zero? So when will the bug be left of the lamppost that's at zero? We got negative 32 feet down here, maybe 40 feet or something up here. So when will it be left? Well, that's when the blue graph is below zero. And that happens from time 0 until 1 second. And then we go back negative here at the 4 seconds. And then it goes back to the origin right here at the, at the 8th second, I believe. So at any rate, what we have is, what was it saying? When is the particle to the left of zero? It's whenever the blue graph is below zero. That's when we are to the left of our reference point. When will the particle not be moving? That, you can either get that at the local max and the local min of the blue graph, because you know that's where the bug stopped and turned around, or probably more appropriately, it's when the first derivative, the red function, is equal to zero, which, not coincidentally, but because of the tangent line being zero, is at the local max and at the local min. So set the first derivative equal to zero, that's when the velocity is zero, the particle is not moving. So at what times will the particle be moving to the left? Well, that's an interesting question. The particle is moving to the left when the velocity is negative. So if we look here, that's when the red function is below the x-axis. So the particle's moving to the left when the velocity is less than zero. So we can see that. So use your calculator on these problems and take a look at each graph and write them down, jot them down if you need to, whatever. Now, what about the time when the particle is moving toward the origin? That's a little bit sneakier. So here's the deal. Do you agree that if, let's just wrap our brains around this first and then see how it affects the function. So check this out. If the particle was sitting to the left of the origin, then it would be moving towards the origin if the velocity were positive. So if you think about what that means, if the mosquito here is to the left of the origin, that would imply that the distance function is less than zero. Now, for it to be moving towards the origin, its velocity has to be going in a positive direction. So that would mean that, so we could say, and, okay, why did I do that? So, and the velocity would have to be positive. Okay, so that's one scenario. The other scenario is the mosquito could be to the right of that reference point, to the right of the origin. If that's the case, for it to be moving toward the origin, its velocity would have to be negative. So when that happens, we have the distance of the particle from the point of reference would have to be above zero, but the velocity would have to be less than zero. So there's a simple way to memorize it if you want to. I think you should both memorize and understand. Notice that the distance function sign and the velocity signs would be opposite. If you're to the left of the origin, but you're heading to the right, you're heading towards the origin. But if you're to the right of the origin, but your velocity is in a negative direction, you're heading to the origin. So it's when the first and second derivatives have opposite signs is when you're heading towards the origin, towards the reference point. Okay, let's look at some other fun problems. How about the time when the particle is speeding up? All right, remember what speed is. Speed is the absolute value of the velocity function. So, let's think about this. Let's draw again where the lamppost is. Here's the lamppost, that's at zero, and the bug could be down here, or the bug could be over here. Okay, so now let's think this through. If the bug is to the right of the origin, or anywhere, if it's heading to the right, I should say, and the acceleration is positive, then it's heading to the right and it's speeding up. Its velocity is going more positive and it's heading to the right. So if the velocity was greater than zero and the acceleration is also greater than zero, then the bug is heading to the right and it's speeding upward. Now the other thing that could happen is, Suppose the bug is heading back this way. Well, that's negative velocity. So let's see what happens if the bug is heading in a negative velocity situation. If it's speeding up, then it's got to be, its acceleration has to be a bigger and bigger negative. It's got to be going in the negative direction. So if it's speeding up, the acceleration in this case would also be negative. So put those two ideas together. When the when the first and second derivatives both have the same sign, that's when the particle is speeding up. If we look at it on the graph over here, look at the red and the black. When the red is positive, when the red is above the x-axis, that means the velocity is positive, the particle is moving to the right. And when the acceleration is also positive, it means the change of the velocity is going in a positive direction. Acceleration is the rate of change, It's how the velocity is changing. So if the velocity is positive and it's changing in a positive fashion, that means the velocity is positive and it's also increasing in the positive direction. So both signs the same as it's speeding up. Now go down in here. Down in this portion of the graph, right down in here where the red is negative and the acceleration, the black is negative, that's when the bug is moving to the left and the velocity is also increasing in the negative direction. So what does that mean? The velocity is heading negative and it's speeding up in the negative direction. So when the first derivative, the velocity, and the second derivative, acceleration, both have the same sign, that is when we're speeding up. So when are we slowing down? Okay. So that is when the two have opposite signs. So if the velocity was heading in the positive direction, but acceleration is negative, that means the velocity is slowing down, it's concave down. So the speed, the net result is that particle is slowing down. But if the velocity was negative and the acceleration was positive, that means the bug is moving to the left, but it's also slowing down because a positive acceleration means it's working towards turning around and heading in the opposite direction. So it's slowing down when the first and second derivatives are opposites of each other. So right up here, if you look at the first few seconds of this bug's travel, remember how it started to the left, it was heading towards the lamppost, so its velocity was positive, the red was positive, but remember it was slowing down, it was concave down. So eventually it was slowing down, it was going to turn back around. So the velocity was positive, but the acceleration was negative, so when those are opposites, then it's slowing down. And then finally, nope, we got two more. Tell the time when the particle has the greatest speed. Speed is the absolute value of the velocity. So we look at when is the velocity function the furthest away from the x-axis. It reaches a negative velocity down here, maybe at negative, 12 or something like that, but it gets much further away from the x-axis. These positive velocities are having the bug go a lot faster in the positive direction than it was heading to the left down here. So the greatest speed is the greatest absolute value of velocity, and absolute value is distance from zero. So distance from the origin, from zero, are you a further distance in the positive direction or the negative direction? So I think you can reason that through. Speed is the absolute value of velocity. We have the greatest positive velocity up in here, the greatest negative velocity right here. This negative velocity is nowhere near the speed of that positive velocity on the red curve up there. Finally, the time the particle is the greatest distance from the origin. Well, distance, think about that. You go back to the original function in blue. That tells you the distance from the lamppost. And again, in that interval from 0 to 10 seconds, where the blue function is the furthest from the x-axis means that's when the bug is the furthest from the light post, either in the positive direction or the negative direction. So check the local max, the local min, and the endpoints, and it does look like the endpoint up here after 10 seconds, the bug is going boop, then woohoo, it's really taken off to the positive direction. So it looks like its greatest distance from the origin is going to be up here when t is 10. So plug 10 seconds into the original function to get the greatest distance from the origin. And again, the greatest velocity is up here at 10 seconds. So going back to this one, where's the greatest speed? Put 10 into the velocity function to see what that positive velocity was, and that's the greatest speed. So all you need to do, keep track of these three functions. The original function is the distance from the lamppost, from the origin, from the point of reference. First derivative is the velocity. That will give you the speed. That will give you how fast it's traveling, either in the positive or negative direction. And the second derivative is the acceleration. Are we increasing our velocity in the positive direction? Are we increasing velocity in a negative direction? Are we speeding up? Are we slowing down? So there's a lot to think of, but remember these three graphs, think logically how they relate, and if you slow down and process it and you truly understand what each of these three functions is telling you, then you can handle just about any question that's thrown at you.